exoplanetary environment. And today I will specifically talk about what we learn from the interior about the surface of specifically rocky exoplanets. And you may wonder why we actually talk about the interior of planets, because I assume that most of you are actually interested in how it looks like at the surface of these planets. We actually even often see these nice, beautiful images in rather outreach articles or blog articles about how the surface of an exoplanet in comparison to our own Earth may actually look like. I do hope that you all know that this is not what we actually see about an exoplanet. The hard fact, the reality is what we actually see is something like this. So we get statistical information, orbital information, we may get an inference about how large a planet is, depending on how much light of a star is actually blocked when a planet is transiting in front of the star. Or we may actually see changes in the light curve coming from the star, which means that there is some mass orbiting around the star and the star is slightly moving in space. But this is like the most information that we actually get out for an exoplanet, at least nowadays. There are also sometimes what we call direct imaging or direct images of exoplanets. Here's an example from the James Webb Space Telescope. But even then, it's at wavelengths that are actually not comparable at all to the optical wavelengths that we typically think about. And it's also just 1 pixel. So we don't see planets. So we need to have other ideas of how we can actually understand what the planets are like, what the atmosphere could be like, what the surface could be like. And for this, we need to know more about the interior. But to be able to understand what the interior of a planet could look like, let's have a look first what are actually the data that we can have in a best case scenario for an exoplanet. So this is really the best case scenario. Typically what we have is maybe the information about the planet's mass and the planet size. So this gives an idea about the density and already helps us to understand if a body that we see could be maybe Earth-like or could be rather similar to the icy moons of the solar system, for example, because it has such a low density that it needs to contain large amount of ices. Orbital properties in general also help us to understand something about if heat is generated in the interior by tidal forces, for example. But we also get an idea about the surface temperature if we don't have an atmosphere or greenhouse gases, just by looking at the distance from the planet to the star. In principle, we can also measure the albedo, or let's say the brightness of the surface of a planet. And especially now with the James Webb Space Telescope, have a better idea of gases in the upper atmosphere if a planet actually has an atmosphere. We can also measure the star a little bit better to get information about the age, about the composition of the star, stellar activity, or maybe even if there's a magnetic field, which can also impact at least some exoplanets if they're close orbit to the star. But this is more or less information that we can actually get for a planet beyond the solar system. However, this is actually not bad. Before the age of spaceflight, this was actually the kind of information that we had for the moons of the outer solar systems around Jupiter and Saturn. And we already had a good feeling about these bodies based on the density, the size, the albedo of these objects. For the atmosphere, again, with James Webb, you probably have all seen this announcement about 2 years ago that the first detection of CO2 outside the solar system was actually measured. In this case, not a rocky planet, not a potentially habitable object, but a hot Jupiter WASP-39b. But it shows us that in principle, James Webb Space Telescope can actually help us to characterize atmospheres and to get ideas of major contributions, which in our solar system, Venus, for example, and Mars, both have a CO2-dominated atmosphere. So we can really get access to some more information since the James Webb Space Telescope launch. But again, we are not talking today about the atmosphere. We are rather talking about the interior, or how the interior actually contributes to the atmosphere. Yeah, so we are talking here now about the interior, and aspects or processes from the interior that have a strong impact on the surface are, for example, a magnetic field. And if you have a magnetic field, depends on if you can actually have convection in some conductive fluid, and typically if you think about it as in convection inside of a liquid metal core. But we also have transport mechanisms in the mantle that lead to the cooling of the mantle, and specifically drive things like production of crust, volcanic activity, so really things that matter at the surface. And we also need to consider what the chemistry of the interior of the mantle is like, to have a better idea of what kind of outgassing or what kind of atmospheres we would actually expect. And why all these things actually matter. We can have a look at our own solar system and compare our own planet, Earth, with Mars, our neighbor planet. Mars is actually much smaller than Earth. It's about half the size. And many of these processes work differently because of that, because of the size. So what you can see on the left side is a rather complicated feedback mechanism between the interior of Earth, so everything below the crust, where we have subduction, of course, recycling material from the crust into the mantle. This is something that's very important for the global CO2 cycling. Of course, the cooling of the mantle is something that helps to also cool the core, and the cooling core, this is what actually drives the dynamo-magnetic field. The magnetic field shields the atmosphere from erosion, or at least in some parts can help to shield the atmosphere from erosion, but definitely it helps us to shield us from radiation from space. But the atmosphere is again maintained via outgassing. So there are a lot of different aspects, processes on Earth that are interconnected with each other. On Mars, many of these processes are missing, and the most likely explanation for it is it's because it is so small, it cooled very efficiently, it likely never had what we have on Earth, this subduction, this plate tectonics mechanism, and most of its atmosphere is actually lost by erosion or other processes at the surface. So to be able to understand which of these processes would actually be active on which kind of planet, first we need to understand what is the planet actually made of. And for this, if you go outside of the solar system, we again don't have much information apart from mass and radius and information of the star. And the reason why the star matters here is that when we think about the evolution of stars themselves from their birth to forming an accretion disk around a star and planets forming in this accretion disk, means that there is actually a chemical link between the formation of stars, the stellar clusters, and the planets later on. And these accretion disks have for a long time been theoretical models, but now thanks to the ALMA array, we actually have visualization. We actually know that these accretion disks exist around other stars. We know how long they exist, 7 million years that we have this gas around stars and planets form within this time frame. So if you actually know that there's this chemical link, we can actually turn to what kind of compositional variation do we actually have for stars. So before we look at the planets, again, look at the stars first. And what we can see here is just one example of the ratio of iron to silicon and magnesium to silicon. These three elements, iron, magnesium, and silicon, are actually together with oxygen the main elements that we have inside of Earth. So they make up about 90% of the composition of Earth is magnesium, silicon, iron, and oxygen. So if you have an idea of how these elements vary with respect to each other in the star, this already gives us some first indication of what the planets could actually look like. Then, of course, if we turn to the accretion disk around another star, we also have to consider that if you are very close to the star, the gas is actually going to be irradiated by the star. It's going to be very hot. So some elements like water, for example, will actually not be able to condense and form planets or contribute to the formation and accretion of planets if we are rather close to the star, which is different if you go a little bit further away. So depending on where we actually are, if we are in an inner part for our solar system, the inner solar system, we would expect quite a different composition. This is actually what our Earth looks like when we model what's the composition from our stars and how it would affect the composition of the planet. And this is how it would look like if you would go a little bit further out in the solar system. So these kind of models, in this case from Alexander Thumb from my group, help us to understand how the composition should vary within the accretion disk and then therefore within the planets around a star. And this can help us to get a first order understanding. One of the main factors why iron actually also matters is because, as we also see in the solar system, actually from stochastic processes, from impactors that happened in the solar system, we can actually have planets with very small matter cores or planets with very large matter cores. So our moon has a tiny core, and Mercury is mostly or dominantly made of iron. And we can, of course, wonder if this has an effect on surface processes, a surface regime, volcanism, and so on. I'm coming back to this in a couple of slides. For this composition, I just want to quickly mention that everything that I'm going to present you today in this lecture is taking a planet to be more or less similar to what we see in the solar system. So this means we assume, for example, that planets are differentiated into a matter core and a rocky mantle. And if they are volatile, then we would have like a water layer or an icy layer on top. And we assume that the most dominant minerals that we have are made of oxygen, together with, again, magnesium, silicon, and iron. In principle, we can have more exotic planets. So there have been studies out there either predicting that we might actually even have carbon-rich end members. So you may have seen these nice illustrations of diamond planets out there. Now, this is not how they would look like, but you can sell it better if you have these nice diamond pictures. We can also have very water-rich planets in such a case that instead of these separated layers, like what I just mentioned before, what I'm going to assume here today, we may actually have water mixed with melt, and so the interior structure and also then the surface condition would be quite different than in these more simplistic models. We don't really know how long such a state would actually be valid, could actually happen. If we go to cooler planets, likely we form a solid mantle, silicate mantle, and if you have enough volatiles, then a water-rich layer on top of it. So if we talk about the atmosphere and what actually influences the evolution of the atmosphere, we actually have to look at different stages. In this case of Earth, of our own planet, starting with that, but for other planets, it should be more or less similar, at least for the first processes. So we assume that the planet is formed at the beginning by accretion of either planetesimals or pebbles. We bring more and more mass together. We may have an atmosphere that is even attracted from the gas, from the accretion disk, which would then be like a hydrogen helium dominated atmosphere, very similar to the main components of the solar atmosphere. We would strongly heat up the interior and obtain a magma ocean. So everything would be molten, or at least a large part of the interior would be molten. We form our core. And this can already lead to an exchange of gases between the accreted material in the interior and the gas that has been tracked from the accretion disk. But at some point, our core is formed. We have our rocky mantle, maybe even some surface liquid water if the temperatures allow for that. At least in case of Earth, this was very shortly after the formation of the Earth case already. And then we have, for a long time span, volcanic outgassing. And so here, this is where the interior really matters strongly for the interior. On Earth, something else happened. We actually had life originating, doing something nasty to the atmosphere, changing its composition, and changing specifically an atmosphere which was maybe having large amounts of CO2. We still don't really know how much CO2 we did have in the atmosphere, SO2 or other elements, and changing it to the nitrogen and oxygen dominated atmosphere that we know of today. So we typically call this a tertiary atmosphere. The volcanic outgassed atmosphere, this is what I typically call a secondary outgassed atmosphere. So this is volcanic degassing. And this is what is actually active probably for most of the time on a rocky planet, unless there is again contribution of life changing the atmospheric components. I'm not going to talk about the magma ocean because I've seen that there's another lecture by Ludmila Karune who's going to focus specifically on this phase. But in general, what drives outgassing, volcanic activity, or even before that mantle convection in general, is heat in the interior. So the question is, where does the heat actually come from inside of Earth or other rocky planets? And the first energy source that we have is, of course, we can understand it quite easily. If we create a planet, we bombard the planet, we bring energy together. And this is actually leading to a large energy source, accretion and heat, we call it at the beginning. When the core is actually forming due to the sinking behavior of the heavy iron towards the center of the planet, we also release energy. We call this gravitational heat, which is released rather at the beginning of the evolution of a planet. And then over the entire duration of Earth, we have a contribution by radiogenic decay from uranium, thorium, potassium, which is actually decreasing in strength over time, but still today is producing about 50% of the energy inside of the Earth. The rest is still cooling from the accretion and gravitational heat. If you think about exoplanets, many of the exoplanets that have been discovered and discussed quite a lot in the recent past, like the TRAPPIST-1 system, for example, so I'm going to come back to also at the end of my presentation, there another form is also very important, another form of heating, and this is tidal heating. Due to interactions of the close orbits of the different planets around the star, they actually tear at each other and therefore heat each other as well. And so we get actually some substantial heating by tidal heating, tidal dissipation, at least for the close-in planets around other stars. And I mentioned earlier that the magnetic field of a star may actually also be relevant. This is specifically important if a planet is embedded in a magnetic field of a star in a way that the magnetic field is changing, fluctuating, and then it can also heat up the planet. But I'm not going to talk more about this today. Now, if you know the composition of a planet, we know how much heat we actually have in the interior, or at least we have estimates, predictions of what the heat could be. We can then use different kind of models, 1D parameterized models, or in this case, 2D convection simulations, where we model how in the mantle material is actually redistributed by convection, by convective motion, very similar to if you have a pot of hot water, you heat it from underneath in the kitchen, for example, you cool it by air from the top, and you actually start to get convection cells. The mantle is acting in a very similar way, but it's actually not liquid. So it's rocks, like really rocks like we have them at the surface, but due to pressure and heat, they're actually deforming and therefore moving and leading to convection. If we actually have material then going towards the surface, at least what you can see here in this simulation, is that if the material is very hot, it's heated up at the core mantle boundary. At some point, it will actually reach shallow pressures where the temperature is so high that the solid material will then start to melt. And if it's actually high enough that this is happening, the melt will rise to the surface. And if we had volatiles in the mantle, take actually the volatiles along and outgas it, so push it into the atmosphere. This, by the way, depends a lot on where the melt is actually produced. If the melt is produced a little bit too much downwards, it will actually sink back in and not contribute to melting, not contribute to outgassing. And so what you can see here is actually a dehydration of a mantle. If the rock started a little bit, was saturated with water at the beginning, and due to melting, you can see this color changes from blue to brown. So whatever volatiles we actually had in the mantle was then redistributed to the atmosphere. Of course, these processes on how to build an atmosphere are quite complex. So we do not only have to take into consideration things like that melt maybe is even heavier than rocks if it is produced too deep into the mantle. We also have to see how many volatiles are actually going from solid mantle into the melt, and this also depends on where the melt is produced. We have to understand what the chemistry is in the mantle, because depending on if we have more oxidized or more reducing conditions in the mantle, so more oxygen or more carbon, for example, this influences directly how much carbon, for example, how much oxygen will end up in the melt, and also what kind of gases we will actually have outgas at the surface. So, for example, if you have a very reducing mantle, Mercury, for example, could be an example for that, or even Mars or the Moon, then volcanic outgassing would be dominated by gases like hydrogen, maybe some water, CO in it, some H2S, for example. But if in the end, if you have a very oxidized mantle, Earth is actually a perfect example for that, and Venus may actually also be closely as oxidized as Earth, then outgassing would be dominated by very different gases, so CO2, water, nitrogen, and sulfur species as well. So this range of outgassing is something that we would also expect for planets beyond the solar system, for exoplanets. And depending on which of these two sites we actually are, we could get very different worlds. So even if otherwise the planets are made from the same, or they have the same mass, the same radius, the atmospheres could be very diverse, going from these reduced atmospheres to these very oxidized atmospheres. And interestingly, depending on if you have such a reduced atmosphere or rather oxidized atmosphere, this also leads to very different atmospheric thicknesses. It's maybe also something that may be measurable at some point. What you can see here is also a comparison of different atmospheres, strongly reduced or to strongly oxidized, so exactly these two end members, and the case in between, the moderately reduced case in between. And you can see that spectra, emission spectra, thermal emission spectra of exoplanets, and this is something that we may be actually able to probe at some point, will look actually quite different depending on what the main composition of the atmosphere is, if it should be carbon dominated, for example, or hydrogen dominated. And again, if it would be an oxidized or reduced atmosphere, so if you would have H2 or water, if you would have CO or CO2 in the atmosphere. And while James Webb Space Telescope may be able to detect some of the signatures for some like H2, this is not possible, but there are some ideas with upcoming mission designs, like for example, the Large Interferometer for Exoplanets initiatives that would actually directly observe an exoplanet in the habitable zone around sun-like stars, would be able to distinguish or should be able to distinguish at least some of these features. So in the future, we may be able to detect these kind of atmospheres. So we now should understand at this point, when would we actually be able to expect what type of an atmosphere. So for this, I'm coming back to these numerical models, so the models of convection in the interior and how much melt is actually produced where. What you see here are actually two different parameter studies where we actually took a planet, our Earth actually, our model Earth, without plate tectonics, so taking it as a stacked and lit planet for simplicity, and thinking about what would actually change if, for example, the core of Earth would be much smaller, if you would have a very small iron fraction of just 5 weight%, or if you would go to a huge iron core. Or the same question, if we take our own planet Earth and we make it much smaller, so Mars mass, for example, 0.1 is the mass of Mars in Earth masses, or go to much higher masses, to super Earth masses. And you can always see two images. One is a snapshot of the interior after 500 million years of the evolution of this planet, or 4.5 billion years, which is the age of Earth. And the color coding yellow tells you that all of the material was molten at some point, and whenever there were volatiles in there, they were actually extracted to the surface. And you can see that in some cases, the interior structure, so the size of the core, but more dominantly the mass of the planet, can really have a major impact on the questions of how many volatiles you can actually put into the atmosphere. So summarizing this in a plot that at least astronomers are feeling more comfortable with, this is a mass radius diagram where you can see for different planet masses and Earth masses, depending on what the composition of these bodies would be, what is the range of planet radii that we would expect. So the line down here would be a planet which is almost composed of iron, and the line up here is a planet where we don't have an iron core at all, and we only have a rocky and silicate mantle. And based off simulations like the ones that I've just shown you in the slide before, you've seen that there are some ranges where we can actually have efficient outgassing. And so our theoretical concept of the habitable zone, where we look at the planet being somewhere at a specific distance of a star, always assumes that we have a large amount of outgassing available. So at least about 10 bar of CO2, so that if you go a little bit further away from the star, the CO2 cycle can actually become active, and we have an efficient greenhouse gassing. Greenhouse heating. But if you actually don't have that, if you have just a little bit of CO2, maybe no CO2, so these are these yellow and reddish areas here, then this may not be given anymore. And so there's a range of planets that seem to be more interesting for potential habitable planets. However, there are a couple of caveats there. These models did not include, for example, if there is still a primary atmosphere from this magma ocean stage or from the accretion of the planet. There may also be some late info of cometary material still leading up a little bit of an atmosphere. So to be honest, impactors may also erode an atmosphere. So this is a question if it's a friend or a foe, if you have cometary material being accreted later on. But we may also have plate tectonics. And plate tectonics may actually change this image quite dramatically, because if you have plate tectonics compared to a stagnant lit planet, it actually means that we stir up the entire mantle and we push plates into the mantle, which means that we're actually creating active ridges where plates are spreading away from each other. So hot mantle material can go to the surface, and we will for sure have melting there. But before I come back to the effect of plate tectonics, just quickly, because I had mentioned the magnetic field in the beginning, that it's also related to the interior. We had also looked at a subset of planets, so going here only from 0.8 to 2 Earth masses, looking at, depending on the interior structure, again, if we have a stagnant lit planet, how much heat can actually efficiently go out of the core, and how long can we actually drive a dynamo this way? And in a recent study, we could show that there's also, depending on where you actually are in this mass radius diagram, there are some planets that may more easily be able to keep a magnetic field than others. I should say that the bluish cases here, it doesn't mean that they don't have a magnetic field. It just means that the core needs to have additional constraints to be able to generate a magnetic field, like on Earth, where we have a chemical dynamo acting on Earth today. Yeah, but coming back to the plate tectonics, as I just promised beforehand, again, we would actually assume that if you have plate tectonics, then these constraints, this mass constraint or interior structure constraint for really efficiently building up an atmosphere that can lead to a strong greenhouse effect or a strong enough greenhouse effect in the habitable zone is actually quite easily satisfied. So you may actually wonder right now, how likely is it then to have plate tectonics? Does this maybe depend on planet mass or not? This is a very obvious question, and this has actually been addressed about 15 years ago, or a little bit more than 15 years ago. The first studies thought about, well, if you do make like a plot where we have Earth, one Earth mass, we put Venus here, a slightly smaller mass, Mars has a very, very small mass, and we look at what we see about if they have plate tectonics or not. Mars doesn't show any signs of plate tectonics, and for Venus, there's a debate. We are not quite sure. So there seems to be some kind of a trend that we see there for the likelihood of plate tectonics, and so we can then wonder if you go to higher masses, how would this continue? And maybe the evidence from the solar system would point to even higher plate tectonics likelihood if you go to higher masses. And this is actually what this first study in 2007 predicted. The main problem was in the same year there was another study saying actually it's more or less the different outcomes. So larger planetary masses should actually lead to an isolation of the surface and the mantle. And a few years later, there was another study saying, nah, the mass actually doesn't matter, it's water that matters. And some more studies looking into this in the years after that. You may think that these don't agree with each other, but the thing is actually the problem is that there are so many more factors that influence if you have plate tectonics or not, and not the mass alone, that depending on what kind of assumptions we use in each of these studies, we actually do get different trends. So let's just say it this way, it's not only the mass that matters, so we cannot yet predict for an exoplanet the chances for having plate tectonics. What we can do is we can assume it has have plate tectonics, and we can assume it does not have plate tectonics, it has a stagnant lid, and see how this actually influences the interior dynamics and also the outgassing. And what you can see here specifically, if you look at the lower plot, is over a range of planet masses, what is the depletion efficiency, or we can call it outgassing efficiency, like how likely is it if you have volatiles in the mantle to actually get them out into the atmosphere and build an efficient atmosphere for plate tectonics planets in comparison to stagnant lid planets. And we see that we have quite a bifurcation here between these two cases. This would lead to different amounts of gases that can be outgassed. Just as a quick note, if you wonder what this means, total outgas pressure by no means is the atmospheric pressure that you have, but it means what if all of the volatiles would actually really degas into the atmosphere unhindered, how much would this actually accumulate to? But of course, we have erosion of an atmosphere. We have different ways of bringing, for example, with the carbon silicon cycle, volatiles back onto the surface. So the actual atmospheric pressures will, of course, be much, much lower than that. So I now talked about all of these different mechanisms, the processes that relate the interior to the surface. I just want to make a quick summary before I go to some other slides looking at the atmosphere of the different planets. So for the interior processes, how do they actually depend on the size of mass of the body? If you look at convection of the mantle of the rocks in the interior, which is actually the driver of all of the other processes, if you go to very small bodies, so here I had the moon or Mars as an idea, as a picture, we won't have that much or not for a long time scale convection in the interior. If you go to an Earth-sized planet or even larger planets, this is not a problem. If you look at the chances to actually generate a magnetic field in the interior for a long time scale, then again, for the small bodies, this doesn't look too good. They just cool way too quickly. For Earth, I put a yes there because Earth apparently has a magnetic field. Venus, on the other hand, has the same size as Earth, does not have a magnetic field. And if you go to larger masses, it depends again a little bit on other processes, but they can have a magnetic field, but it's not a given that they do have a magnetic field. Active volcanism is something that, again, for the very small bodies, very quickly, we will have strong active volcanism at the beginning, but then it will decline. As of over long time scales, we will not expect active volcanism. For Earth, obviously, or Venus, this is different, where we do have active volcanism. And again, if you go to these massive planets, this depends on other things like plate tectonics, for example, if you will have volcanism or not. For atmospheres, I talked about that we may have erosion of an atmosphere to space, which is why for like a habitable planet, we need to be able to replenish gases into the atmosphere. But on the other hand, if we go to very massive planets, we may have the opposite problems, that we may accumulate too much of an atmosphere. And then even though this planet may be in the habitable zone, may not actually be habitable because of a too thick atmosphere. So this is a problem that we can have for this massive planet, specifically if they have active volcanism. But again, for the small mass planets, the moon doesn't have an atmosphere anymore. Mars has only a very thin atmosphere. Yeah, and again, for the plate tectonics, again, for the small mass planets, not ideal for plate tectonics. Earth-sized planets pretty much, but again, Venus doesn't show active plate tectonics right now. And for super Earth, it's again a question. So you can see that by looking at these different processes, how the interior influences the surface, there's some range of maybe not exactly one Earth mass, but maybe Earth mass plus 2 or 3 Earth masses, something like this, where the processes seem to be more ideal to produce a habitable planet. And so there's a good reason why when we look at exoplanets, we talk about things like an Earth similarity index related to, for example, the mass, radius of the planet, or the surface temperature that we receive, because it really seems to be that there is some Goldilocks zone in planet masses, planet sizes for producing a potentially habitable planet. Yeah, and this we can then apply to all these different exoplanets that have been detected out there and see which one might be more likely habitable or not. So I want to conclude now with a couple of slides on what kind of atmospheres we should actually expect for these diverse exoplanets that we might have out there. And I will start with looking first at the solar system. I mentioned before already that Venus and Mars both have a CO2-dominated atmosphere, whereas the atmosphere of Earth is much more evolved. We have different signatures in the spectrum, not only from water, but also from ozone, for example. O2 is something that we don't see in the atmosphere. But what we can wonder, what other types of atmospheres can we actually have? If we look actually in the entire solar system, including our sun itself, we have essentially 3 different types of atmospheres. One is for the gas giants and for the sun itself, made mostly out of hydrogen and helium. Then we have the Mars and Venus case that I mentioned before, where we have the CO2-dominated atmospheres. And then Earth again has a nitrogen-oxygen atmosphere. And Titan, an icy moon of Saturn, even though it doesn't have oxygen, it also has a very nitrogen atmosphere. So it also seems to have some kind of similarity, and that's why often people say that Titan may be like a key in Earth's laboratory to understand what kind of periodic chemistry is possible in these kind of atmospheres. The main difference specifically for Mars and Venus is actually the atmospheric pressure. Sorry. So we can then wonder how does actually the atmosphere or what other kind of ranges of atmosphere could we predict beyond what we actually see in the solar system. And what we can see here is the chemical abundance that we actually have from inside of our universe, where most of the elements are hydrogen and helium. And the other elements mostly are oxygen, carbon, nitrogen, sulfur, and phosphor. And this is quite interesting because when we think about atmospheres, these are actually the components that are most relevant for an atmosphere of a planet. Just as a side information, if you look at the composition of life on Earth, in an average, the most dominant chemical elements actually also oxygen, carbon, hydrogen, and nitrogen. By coming back to the atmospheres, from an outgassing point of view, we can actually expect quite different types of atmospheres to form, depending on what I mentioned at the beginning, if we have a reduced or more oxidized mantle. So I had these 2 end-member cases before. So we can see that what we actually outgas could change quite dramatically. But another thing that matters is the so-called outgassing pressure. So, for example, if we have a layer of water on top of our volcanoes at the surface, the gases that will come out will be very different to if we have subaerial volcanism, so a volcano directly in contact with the atmosphere. For example, water is something, if you have a higher and higher atmospheric pressure or lithostatic pressure, at some point water will not be outgassed anymore. Something else that then influences the atmosphere, so it's not only the outgassing alone, but we also have to look at where our planet is, at which distance from the star. Because if you're going very close to the star, no volatiles will be able to remain around a planet. They will escape very quickly. But if you go further and further away, at some point, we can have water stable at the surface of the planet, like where we have for Earth and Mars. it's a case. Or if we go further away, Titan is here a good example. We will actually not be able to have much CO2 in the atmosphere anymore, and this also changes the atmospheric composition. Interestingly, these different domains that we see here are again the massive planets. So in this direction is a mass. The more mass it is, the more easier it is to keep lighter elements like in hydrogen and helium accreted together with a planet in the beginning, the first evolution. Here in this range, we see these Venus-like planets, the Earth-like planets, and Titan is right here. So just from the theoretical concepts, what we see in the solar system is exactly what we would predict. So how is this outside of the solar system? And there, the best system to look at is actually the TRAPPIST-1 system. So again, from these most likely candidates, again, it's a little bit boring, but the most dominant atmospheres that we would actually predict from models are the ones that we see in the solar system. And so what do we see about the TRAPPIST-1 system? Just quickly for those of you that don't know it, so I don't believe many haven't heard of the TRAPPIST-1 system so far. The TRAPPIST-1 is an M dwarf about 39 light years away from our sun. And it actually has 7 planets in a very close orbit. Actually, the orbit is as close approximately as the moons of Jupiter. And also the size of the star is not much larger than Jupiter itself, but it is a star. And by now, James Webb Space Telescope has actually seen all of these planets, and the data are still being evaluated, but we have some first indications for the first 2 planets, 1b and 1c. And for TRAPPIST-1b, you probably have all seen this also last year, the big announcement that with TRAPPIST-1b may actually not have an atmosphere. And this is actually based on one measurement point. So this is actually what has been measured. This is the signal that we would actually get with the 6 CO2 atmosphere. This is a signal that we would get without an atmosphere. So just based on this one measurement point, one may expect there not to be an atmosphere around TRAPPIST-1b. Of course, we need multiple measurements. We can also have CO2 atmospheres with hazes that would also give us a signature similar to what has been measured. So there's still some evaluation going on right now, but it looks like TRAPPIST-1b may actually not have an atmosphere, or maybe just a very thin atmosphere of CO2 with hazes. What about TRAPPIST-1c? For TRAPPIST-1c, we also have only one measurement so far that has been published. And this would actually also work with a bare rock surface, so a planet without an atmosphere, or with a very thin CO2 atmosphere without any clouds. So also here, there's some new data coming in, being evaluated right now. So we will probably hear more in the next couple of months about these 2 planets. But to be honest, so far, what we would predict for these planets would be either CO2 dominant atmosphere or no atmosphere. And this is more or less exactly what we see in the few data points that we have so far. But let's see what's coming in the next years for further observations. Yeah, and so with this, I leave you with a summary slide and maybe stop already now so that we can have some discussion.